chips doubles every 2 years. This is a phenomenon that is currently getting smaller. It's not an absolute law anymore. And that's mostly because the reasons we can see in this diagram here, we can see that although the number of transistors is getting bigger, we have stable single thread performance, we have the maximum frequency, we can't have bigger frequencies, the typical power is also the same, and the number of logical cores is growing. This is because mostly our current innovations around making transistors smaller is getting very difficult. Each time we try to make a transistor smaller, the research and the money needed in order to break through and make new innovations are getting doubled each time. So it's getting really difficult to create smaller and smaller nodes. And we have the current state of the market everywhere, from data centers and high-performance computing to networking to automotive, through financial services, healthcare. Everyone wants smart futures, wants machine learning algorithms implemented on their systems. This happens because of hardware and software advances that fuel the competition between companies that try to compete in these markets. Today is the era of big data, of high-performance computing, and AI everywhere. Well, what's happening beyond Moore's law? We have a lot of disruptors. We have end-to-end energy efficiencies. We have the silicon health and yield. We have multiple die design. We have cloud infrastructure. We have increasing software content. We have DevSecOps. We have increasing risk. And also, we need a lot of engineering talent, and we have AI algorithms everywhere. That is how the companies try to innovate in order to have disruptors and make better and custom products for their customers. Another problem we have is that each year that is passing, we have bigger complexity. Our circuits, our logic designs are getting a lot more complex and need a lot more hours, a lot more human hours needed in order to complete and verify a design. Also, today's circuit design needs a lot of innovations needed from the industry. We have photonic chips, we have 5G, we have a lot of innovations, a lot of concepts, a lot of things that a business must have in order to be able to compete with other big players in the market. And that affects machine learning algorithms that are being implemented, of course, affects the data that we can process, and affects how scalable our infrastructure of our business is. Because if we really need to touch a lot of people, we need to have scalable infrastructure. So the macro trends of our market are differentiation through innovation. In order to achieve this innovation, we need chip differentiation. And chip differentiation offers optimized software, hardware, and can drive business success. So how do we achieve accelerating AI algorithms? Well, it's all about concurrency and parallelizing our computations. You can see that we need instruction level parallelism, thread level parallelism, data level parallelism, and task level parallelism. And we have a lot of different types of accelerators. We have from high performing accelerators that are being used as an ASIC. That's something like the Google TPU. Or we have general purpose accelerators, mostly used in AI accelerators inside our phones. Of course, specializing in a way or another is something each designer must carefully choose, because programmability and efficiency are two things he must design in order to achieve a better result. task level parallelism is when we have a lot of tasks that can be accomplished together instead of having multiple tasks waiting their turn in order to be accomplished. That way, we can have a task finished earlier. That way, we can have more data processed. That way, we can be more competitive. Also, we have parallelism in the data level. That is being through carefully deciding what our architecture will be. Most accelerators today use SIMD or a single instruction, multiple data architectures. We have a single instruction that can process multiple data inside of memories and caches. Instruction level parallelism is being done through many pipeline stages. Of course, designing pipeline stages is a difficult concept by itself, because if we have too many pipeline stages, then we have a lot of problem if something happens and we need to empty the pipeline. So our processing needs to be start over. And if we have too little pipeline stages, we don't have enough parallelizing power. So the designer must carefully choose what the pros and cons of each method are. We also have thread level parallelism, which is the same concept as before. We have many threads instead of a single one. By using multiple threads, we can compute a lot more data more efficiently, rather than having a single thread and having multiple single threads that need to take their turn in order to be computed. I want to discuss a proper example, a real life example. We'll talk about convolutional network architecture, convolutional network implementation. You can see we have the filter, we have the input map, and we have our partial sums. You can see how they are being executed from a block diagram. And this is the path that we'll take inside the processor core. From this example, we can see that we have multiple elements that are the same. The green ones, the blue ones, you can see that are the same. Also, you can see that diagonally, the blue are exactly the same. You can see that the green ones in the first row, the green ones in the second row are the same. This means that we can save resources and we can have a better computation if we save this memory, because today's hardware, it's all about memory usage. Memory is the bottleneck. So by keeping data in the same cache and not refreshing them means lower power. Lower power, better processing power means a lot of faster computations. So the grand scheme is having our configurations properly designed. We have our hardware resources, and then we have a compiler designed to optimize our design in order to have the data properly assigned inside our cores so they can be processed efficiently and with the lowest power usage we can use. An important aspect in this is the data flow we choose, because depending on what data flow we use inside our chips, we can have different results. Some algorithms require wait stationary, some algorithms require out stationary. You can see that the differences is whether we use our weights to be inside caches or a global buffer, or we choose to have our mathematical operations. I can't find the English word. The mathematical operations in a steady cache, or we have it in a general buffer. So properly designing the data flow ensures that the algorithm we choose is compliant with our hardware, and we have better data processing. So, looking from the bottom down, the important steps are compilation and execution. We need to carefully design our deep neural network shape and size. That's the program. We need to have the mapper, which is the compiler. We have the data flow, which depends on the CPU architecture and the architecture of the AI accelerator. We have the implementation details that are mostly dependent on the microarchitecture. Then we need to have the mapping, which is our binary data. We have our input data. We have our DNN accelerator and the process data that come out. All these need to be in perfect balance. So why do we need so many people in order to design, and why we need so many hours in order to design is you can see it in this picture, because we need to have people that know about machine learning. We need people that know about compilers. We need people that know about architecture, about microarchitecture. We need a lot of different specialties, and we want all these people to work for many hours in order to design and verify and implement such a concept. Another thing that we need to carefully search and carefully design around is number representation. Number representation, whether that will be floating numbers, sign numbers, integers, POSIT, or software-specific representations. I want also to mention BF floats, brain floats, because they are currently mentioned a lot in a lot of papers. And that's because we can represent different accuracy, we have different number ranges, and we have a lot of energy cost and area cost, depending on whether we want to have a better and more accurate result, or we have a better representation of the results, of how we want to have our results. So that's something a digital engineer must look for. Also, the key performance indicators that every machine learning engineer needs to have are model size, the time that needs this algorithm to make a conclusion, the energy consumption, the forecast accuracy, of course, the area of the chip and the power output, the delay, and the productivity. So why do we need Chipyard Framework? First of all, Chipyard is made from Berkeley Architecture and Research Lab. There are a lot of contenders out there, NVIDIA from NVIDIA, Meridian, Weaver, and a lot more. So why do we need Chipyard? All these systems are good and they can make a lot of great designs, but they lack full system and full stack reconfigurability and parameterization. And what do I mean by that? First of all, let's talk about performance effect. There are a lot of problems designing an AI core. That's resource contention, cache coherency, miss rates, latency, page fault, TLB hits, unaccelerated kernels, interrupts, context switch fields, and so many more. Every concept we talked about before needs to be properly parameterized in order to be our algorithm to be properly executed, in order to have the best possible energy cost and the best possible computational cost. So talking about Chipyard, we have a ready-made ISA. The ISA is properly configured, is properly tested, is properly verified. We have already made hardware configurations that are fully parameterized, and we can change them in our demand. So we have medium software frameworks that can help us design our algorithms. And of course, we have already high-level frameworks like TensorFlow and 1X that we can use and are already used by the market in order to design the algorithm we need that fits our needs or our customer needs. So how is this framework architected? First of all, we have our tooling. Our cores are written in Chisel. That's a Scala language. We have our Fertile. This is the compiler. It creates an intermediate language from Chisel. And from Fertile, we get Verilog. And we also have our RISC-V architecture. We have our cores. We have the Rocket Core. That's a simple 5-stage in order core. We have our Boom Core. That's an out of order core. We have many accelerators, like we'll see, and we have point-to-point network access like tilings. We have caches, and we have peripherals. We also have a lot of flows. We have the parsing framework. It's a framework we can use to properly verify our designs. We have the hammer flow in order to convert our Scala or Verilog or system Verilog files into transistors. And we finally have software RTL simulations through open source and less open source tools like cloud source, like Synopsys VT's software. Rocket Core, like I said, it's a 5-stage in order scalar processor core. It was developed at UC Berkeley, and it's supported right now by Sci-Fi. It's a component we use inside an SoC generator. As you can see, it's fully parameterized. We have the Rocket Chip. Rocket Chip, it's an SoC. Again, we can have many different peripherals and use them in conjunction with the Rocket Chip and create a more complex and more sophisticated SoC. Then we have a Boom Core for our most advanced needs. It's an out of order, fully synthesizable and parameterizable RISC-V Core. Of course, it's written in Chisel hardware language, and it serves as a better drop-in replacement to the Rocket Core. Constellation, it's a network of chips generator. It's used in order to properly connect point-to-point IP blocks in order to have properly verified and correctly done implementations of our chip. Tiling is the cache coherency and memory protocol used by Chipyard generator, and cache coherency is a very important concept when talking about AI accelerators, because we have so many caches, and these caches need to be coherent and need to be properly designed in order to have our data not get garbage data inside. We have caches, memories, and peripherals that access this memory and these caches. And of course, we have DMA that needs to communicate with each other. So we need to have our memories very good designed in order to be properly coherent. And finally, we have our AI accelerators. First of all, we have the Hawacha, if I'm pronouncing it correctly. It's a precision reconfigurable vector architecture. And we have Gemini, that's a full system, full stack, precision reconfigurable deep neural network hardware platform. As you can see, it can have many different data flows. It can have different sizes of level 1, level 2 cache. Its connection to the core and its connection to the SoC is fully parameterized. We can use different point-to-point protocols. We can change the memory size, the scratch pad, and we can change the way the systolic array is used. And also we can have custom IP blocks in order to properly compute more advanced machine learning algorithms. It's a complete framework. It can make a lot of methods, machine learning methods, and implement them correctly. You can see the architecture overview of Gemini. We have our tiles. We have, in this case, an Axelite interface connecting to the system bus and to the control bus. And we have a tier link to AXI bus connecting to memory buses and peripheral buses. So you can see how it's an architectural overview, how it shares its data between the CPU. This is through the shared level 2 cache. We can have data sent from and to the AI core using the shared level 2 cache. And here you can see that is fully parameterized, as I said before. It can use right now 2 data taxonomies, that's built stationary and non-built stationary, but that doesn't stop anyone from creating his own unique data flow or his own unique extension in order to amplify its power. As I said before, there are many CPU to accelerator coupling types, and these types can be properly configured in order to have our system properly designed for our own designs, for our own concepts. And there are a lot of peripherals like UART, JTAG, GPIO. So combining our AI cores with our CPU cores, we can make a shared level to cache, and then we add our peripherals. That's how we create our final SoC. In order to verify that SoC, we have many options. We have, of course, JTAG, the market acceptable verification protocol right now. And we also have tethered serial interface and debug module interface. These are these 2 interfaces used specifically in the Chipyard Framework in order to verify our designs. You can see the differences in the image here. And finally, Chipyard includes a flow in order to verify a design after the tape out. So we have our chip ready-made, and we can use an FPGA, and we can use properly defined procedures in order to verify our design. Thank you. Let me see about your questions.
Actually, I have a question. My name is Mahmoud. So, actually, so we used Chipyard, but there is some lack of documentation. Okay, in Chipyard, for example, how to add interrupt service routine. Okay, there is some topics the documentation is not fully there in Chipyard. Do you see how do you tackle this problem? Okay, I know they have the Chipyard Google group, but what are other ways that you do to tackle this problem?
Thank you for your question. Of course, there are many problems with using open source software. That's because the software is open source. There's no one paid for support. One of the common problems, as you said, are the documentation. In Chipyard's defense and my defense, Chipyard has a very well done documentation in regards to other open source projects, but small problems that arise can be solved with they have a Google forum, a Google group you can join in order to ask questions. Of course, you can send an email, but the answer I get in many questions is read the code. So in every open source project, and that's a task suited for a master's student or a PhD student, and for a student generally, in order to better comprehend the code that is out there. It's a task that every student must have, to read a lot of code in order to understand this kind of big designs.
Okay. Thanks.
Any other question? Okay, thank you again.
Do you provide any extra documentation from your company, or you said the website? Does it have different documentation for Chipyard, for example? Or?
I'll copy and paste the resources I have into the chat. Okay?
Thank you. Thank you very much.
May I ask a question? This is Ed from Biotech.
Yes,
Hello?
I can.
Yes, I have to admire, I have to say that with Serious, I'm sorry, I have difficulty to pronounce your name, but I think you did a good job concerning that you are a student still, and you have been covering very comprehensively about how to design uh, a, a digital deep learning chip, acceleration chip with SoC. I think it's a huge project. Generally, in company like Realtek, we usually have about 500 to 1,000 people to do the whole thing. So it's not easy if you want to make it a product. But as a concept proof, then probably there's other easier way to do it. So, but I would say that you did a pretty good job because given the resource you have, and you have covered all the key factors for the whole design process. I think that's very good, very impressive. And thank you. I learned a lot today. Thank you.
I thank you too.
Hello? Hello?
Thank you. Thank you for your kind words.
Okay. Okay. But I think I would say that the design for DOA, we have a different perspective. One of the perspectives say that we want to do some kind of computation equivalent, meaning that we are implementing some kind of computation engine to make sure that the algorithm can be processed differently, more energy efficiently, or less, reduce. You can reduce the memory access, things like that. So you have a computation equivalent result. And there are higher level design that you were doing not computation, you were doing function equivalent. You know what I'm saying? Like you want to do convolution, you want to do a convolution over certain image, and maybe to classify the object, or maybe to do facial recognition. Then you can do design that's functionally equivalent, but not computational equivalent. You understand? Okay. Then you can also do a task equivalent, or even more up to a level what we call objective equivalent. You understand what I'm saying? So when you were doing usually you will need to have some kind of computation equivalent implementation on the cloud, because the cloud, the server on the cloud has to support different kind of operation algorithm or neural network. Like you may start with convolution, CNN neural network, or YOLO. Then you move to currently most of the major model are foundation model. They are implemented based on self-supervised learning or transformer. So they are different. Okay, they are all different. So there's no one single design. So you have to do more like a generic implementation to support different kind of computation. But the design you are approaching today is more like a edge device or edge device, or some kind of IoT device. Then you don't do that. You don't do computation equivalent. You have to move from computation equivalent to function equivalent, or even to task or objective equivalent. That's where you can actually have a big reduction in terms of cost and power efficiency. Does that make sense to you?
Yes, it does. First of all, let me explain that there are a lot of topics like in memory processing, like using HBM memory, that of course I cannot discuss in a 30-minute talk.
Yeah, no problem. I'm not challenging you. I'm just saying that if you really want to pursue this direction, that's where we are today. I'm from Realtek. We have a lot of projects doing AI, and we have different version of AI accelerator. So that's what I'm trying to tell you, that it's not about computation equivalent now. You have to do objective equivalent. then you will start to see the whole system, whole application, not just a computation. Does that make sense?
My idea, my idea beginning this thesis was how we can have data inferred in edge devices betterly, and how can we have betterly computed data on the edge? Because here in Greece, we have a lot of small startups, and my target audience is these IC design startups. So what my key metric in this case was time to market. So this kind of
that's a very interesting thing too. I mean, okay, so because when you talk about time to market, okay, then you have to give up your cost concern, right? I mean, if you want to optimize the design such that the cost is, low enough, then usually what happens is that you will lose the flexibility. Then whenever there is a change of requirement or a change of algorithm, then it will be very hard for you to have a revision in time. You know what I'm saying? So you have to be very flexible. So what most of the startups who want to pursue after time to market or targeting a new application, they ended up to use FPGA for the implementation. But if you want to do an SoC with a good accelerator, usually you have to understand the application completely and algorithm itself as well. It's not just computation. What I'm trying to tell you is that you have to understand the algorithm as a whole or the objective as a whole. But if you want to do time, time to market, then it's always usually about FPGA. And then the challenge today, if you want to use FPGA for a certain deep neural network, then you have to have the technology to do a synthesizer, meaning that you know how to make the algorithm in terms of Python or C to Verilog or VHDL. That's where you can get the low energy and also the very fast response time. Okay, but I think actually I have to admire you that you did a very good job. I mean, Realtek is a big company. We have a lot of engineers doing a lot of things. So there's no reason to compare with the company like Realtek. But I have to say that you did a pretty good job. I'm just trying to tell you that we have now we have different perspective on this thing now. Okay. So but one thing is that I'm going to give a talk about how to marry AI with SoC or silicon. Okay, and we have in Taiwan. I'm from Taiwan. In Taiwan, we have a task force actually focusing on doing that, and it's not yet an open source, but we have a lot of design which is kind of share between company that approaching the problem differently. So if you're interested, I think I will ask Paul to help me invite you guys to my talk on this issue. So if you are interested. Does that make sense?
I'd love to. Thank you. Yes, I'd love to. Thank you. Your comments are truly valuable. Thank you.
Yeah. But you are doing a very good job, and I'm actually if my talk in the future does help, then I'm willing to help you guys to work on your project, okay, as a pro bono advisor. Would that be helpful to you?
Yes, that would be really helpful. Thank you.
Okay, good. Okay, yeah, great. Thank you so much. And I learned a lot today as well. Yeah, there was a different process you are providing that's not, usual in Taiwan. So I like that. I love that. Thank you so much.
Coming from you means a lot. Thank you.
Thank you. Thank you.
Yeah, thanks, Ed, from Realtek, and also like thanks a lot, Alatherios. I just like we name you EM in Discord. Yeah, so,
听得到，听得到。对，不好意思，不好意思，因为我答应了他们要给一些 support， 所以 support 了，就是因为那个社团是 Realtek 办。
Okay, Ed, so we are
的另外这个 pet project。
Okay, so maybe we can discuss.
现在就是开始在国外在发酵，所以我必须要花一点力气弄一下哈。好，所以好，我们回来看啊，就是QM 不可能有什么子公司组织图啦。
Okay, so thanks. And also like we don't want to like stop the sharing just like today, and just want to let everyone know that there are different kinds of mentors like Ed in economy. So there are also like some like senior IC designers in the community. So very welcome everyone. You can join for our discussion every week at this timing that we share like 45 minutes ago. So if you are interested in this topic, feel free to join on Discord. I shared the Discord link at the beginning. I will share it again. So you guys can join the Discord and we can keep the discussion there. And also if you are interested in today's speaker's topic, you can join him and also help him to like finish the whole design, and I think that you will also learn a lot. So before we end today's sharing, anyone want to ask any questions here? Okay, so yeah, I think that's it for today. And thanks a lot again, Ian, to sharing today. And hope you guys in the discussion and for our weekly discussion on Discord. Thank you. Thank you, everyone. Have a good one.